All right, guys, let's get started. I think I finished grading your exams, exam two. Check those grades. Those are posted now. Um, so yeah, so we're currently in the last few weeks of the semester, right? I think we have like 3 lectures left today, next week, and the following, and then presentations, right? That's it. And then, of course, the finals week. So yeah, so someone was asking me about the scavenger hunt. So I'm thinking we're gonna do that one the week after Thanksgiving. So that what is it? That Thursday we would do that. Does that sound good? It'll be like a fun thing. Like I said, hiding a secret message, but I do want to get through the high crypto demos, right? And some of you will continue demoing on Thursday, this Thursday. There is a new lab this week. So those of you that have finished, just work on the lab. Okay. It's a good lab. It's a SSL lab. So I think it gets more into applications now. This is more like applications. So it's HTTPS. All right. So today, the next few couple of weeks, next Tuesday, we'll look at applications, how to use cryptography actually for things like defense against denial of service attacks. Maybe you've never thought of that, but cryptography can actually be used for defense. So it's not just about scrambling data, right? And so that's what's interesting about it. We'll cover also like malware detection, right? So there's an application for that. And then the last lecture, the week after Thanksgiving, will relate to blockchain a little bit, right? So I think we do have a course in blockchain for those of you that are interested in that, but I'll just wrap up with that topic. Today is kind of a very important lecture. So there's a lot going on. I'm bringing a lot of things together. Finally, if you remember at the beginning of the semester, I said, what is SSL? Guess what? I can't describe SSL yet, right? Because you don't have all the principles and primitives of SSL. I can now today describe SSL. And, short story is you already know what SSL is, right? Because that's what we've been doing all semester. But we're going to tie it to TLS and what TLS is. And everything comes together, even elliptic curves will come into play. So there's a lot little, not miscellaneous things necessarily, but just a whole bunch of things coming together. Okay, so that's really the plan for the discussion today. So I am recording, and like I said, we're having a new lab, kind of like a really nice lab, I think. That also ties in to this. So you guys are 350. Let's take a look. Oh, sorry, you guys. There we are. So let's go to the table of contents just to see where we are. And so exam two is done, graded. So some of you are still finishing crypto demo. Remember, this is really important that you do this correctly. Okay. So we need to finish these. If you've done the demo but you haven't submitted your report, please do so. Because I'm stuck there. I can't grade you until you do that. Okay. Um, certificate authorities. Yes, go ahead, please.
We forgot.
Uh-huh. It's closed.
Yeah.
Okay. Did everyone else submit it? Or some of you did? Okay. Yeah. Send me an email, please, and I'll extend the submission of the report. Okay. If you've demoed and submitted the report, you should have your grade already. Okay, but I do need that report. Any questions on that? All right. And everyone needs to demo. Okay, so if you don't demo, you're going to get a 0, right? Just submitting the report is not enough. This is the homework assignment where you do need to demo and show that you understand the process. Yes, sir. Thursday. And those of you that have already demoed can just work on the new lab, the OpenSSL lab. Okay? Yes. Thanksgiving, right? So no, it's gonna be 2 weeks. Yes, sir. Good point. Usually I would demo the lab, right? But if you can do it on your own, It's not a difficult lab. I mean, it's actually one. It's if you like tutorials, it's like the one that's like a tutorial. But there's a few. What I do in the class is like there's a few points where you might get confused, so I need to like stress on it. But it's essentially creating a certificate authority. You're going to create a client and a server, kind of simulated, and you're going to be sign the keys and all that whole process. It's a really nice lab, and I'll talk about it in a second. But yeah, I guess if you can do it on your own, stay at home and do it there. We've done this lab, I believe, right? And we completed this one, didn't we? The digital signatures, performance also. Is this what we did some time ago? Okay, I guess I forgot the submission. Let me add that here. So this is it's OpenSSL, I remember. Digital signatures. So I'll give you plenty of time. I mean, at this point, I'll give you guys plenty of time for this. So today is what, the 18th? Thanksgiving is here, so let's make it to the 4th. November. Thanksgiving is so it's just November 4th, okay? So you have plenty of time to submit this one. There will be a bonus lab also for those of you that have missed one. It's a hard one, but there will be a bonus one. Yes, please.
The bonus lab going to be the like breaking the digitally generated key that we talked about a while ago, or that's
Oh, that was actually another bonus one. Did you ever finish that one? I assigned that, but there were no takers.
fine.
Yeah, so if you solve it, submit it, bonus points. And that's a fun one, actually. So do that one. All right. Yeah, let me just make sure over here. Guys, any questions? Guys, all right, so November, we said 4th. Complete the attached Word document. And I'm pretty sure I did this in class already. So did this one. So it was the performance one. So I gave you this algorithm and the commands for this, and I did this one. And then you had one problem to work through with your partner, right? So that one is more of a simulated certificate authority, just using OpenSSL. And then the one that we're going to do this week, you're actually creating a proper certificate authority in Linux. So this is with OpenSSL. All right. So this one is done. Crypto Dome. Well, most of you have submitted. Project, another reminder, please. You need to form your groups of no less than two, no more than three. We've talked about this several times, right? This is outside of class. Essentially, you need to pick a topic related to cryptography, and you need to do a presentation, like if it's an algorithm, discuss the algorithm, and then demos. You don't have to code, so it could be something that you installed on Linux, for instance, but it has to be related to cryptography. Hopefully something new and interesting, right? So some ideas I gave you guys are go in depth on elliptic curves. Today I'll do the only elliptic curve lecture in this course. So there's plenty to look into. Students have done this in the past, really gone in depth. You can look at more blockchain, just don't go into like the financial aspect of it. You would have to go into the technical aspect of it. Quantum is a big one. I'm actually going to talk a little bit today, not about quantum, but some of the drivers, some of the fears, right? Something called forward secrecy. So we're going to talk about that and what that means. Okay? Any questions on the project? Remember, you need to do a presentation the week before finals. Okay, so it's worth 10% of your grade. And this is your opportunity to do some research on cryptography. All right, so let's take a look here. So we talked about that. Exam 2 is done. Public key cryptography, this is where we are this week. So this is our module. Notice what we have left is the scavenger hunt. Just said that's going to be the Thursday after Thanksgiving, which is good because we don't have a lab that week. That's the blockchain lecture. So there's no lab with that. And then there's some applications that we will be discussing, as I said, how to use cryptography for malware detection, how to use cryptography for defense of, for instance, from a denial of service attack, the blockchain lecture, and that's it. And then this big num crypto is your bonus lab. So if you want to start, if you've missed a lab and you want to make up some points, this is your opportunity. Just keep in mind, I'm not gonna lecture or demo or anything like that. It's entirely up to you to do it. But it's the same principle as the main idea is you're using C, the C language, so that you can use big things. And so it needs to be fast. That's essentially what it is. Any questions? All right, good. So now let's kind of focus then. So we've talked about the scavenger hunt coming up, and then this is what we're doing this week. So we're going to talk about, we have a lab, which is this one, this PDF. And basically, you're going to be setting up a public key PKI infrastructure. So you follow all these instructions, set up a whole bunch of folders. It's an entirely open SSL lab, no coding on this one. But you essentially are going to have a client, are going to have a server. That server, let's say, is pretending to be Amazon or something, so it needs to have a public key. So that public key needs to be signed by a certificate authority. So you need to create a certificate authority. And in any company, in the intranet, for instance, you can create a certificate authority for that company. So your company in the intranet can have its own certificate authority, for instance. Yeah, so you follow these instructions. So this relates to when you go to a website, and I'm sure this has happened to all of us. We go to a website and the browser says something like, hey, I don't trust this site. You should get out of here. And it gives you some options. And one of the options says add exception, right? And when you add the exception, then you get to go to that website at your own risk, right? Because it's not a trusted key. That's exactly what this lab is about. So you need to sign the keys and add them to the browser so that when you go to that, you don't get that, message, and instead you're able to just access the website. The whole process works just fine. Okay, so that's essentially the goal of this lab, and you complete it until here. So you don't have to do task 4, which is deploying certificate in an Apache-based HTTPS website. You don't have to do this. Now, some students have done this for the term project. So taking it, but then you're using, an actual web server like Apache, and you're doing the whole thing. Here it's a bit of a simulation, but a very realistic simulation. Okay? Any questions? So yeah, so the key thing is you don't have to you complete the lab until this step here, and you can skip the rest starting from task number 4. Questions about that? It's one single problem, maybe 2, because I think it does have the same logic that we've been following all semester, where we would do something, we would do the cryptography, and then we would say, okay, now repeat the whole thing, but change one bit. What happens, right? So it's essentially one of those. But it's a whole one single problem, I would say, but with a lot of steps, okay? All right, so this is the lab, and I'll come back to it at the end of class today, but I usually like to motivate All right, and then the other thing we're going to talk about, I provided this link here so we can do our conversation with this one. Let's start here actually with TLS. So this takes us just to our familiar repo for cryptography. And then I added, I have the same notes that we discussed in class, but I have one section here that it's really important. And it's this one, OpenSSL, right? So this is our discussion. So I'm going to switch back to the whiteboard soon so that we can start looking at SSL more formally and everything. But let's just talk a little bit about this right now. Okay, so, and we'll play with these commands a little bit. So just first of all, some information on OpenSSL. So OpenSSL lets you generate RSA keys. You guys know that, right? So that's what we can do a lot of cryptography with it. Keep in mind the smallest keys that it lets you generate are 31 bits. So that's the absolute smallest that it will allow you to do. So in the command, something like open SSL gen RSA 31. Okay. Now, for this discussion, I'm actually going to talk a little bit about elliptic curves now, right? And so I'll state here that elliptic curves can be faster than RSA because it uses smaller numbers, right? This is key, right? So if you notice all semester with cryptography, it has been this balance between the security and the speed of processing, right? That has been key. And RSA, you guys have seen, it's amazing, right? It's almost like, wow, what a beautiful thing. But the problem with RSA is that we constantly have to have really large keys, right? Very large, 2048 and so on. And so what if you had a situation where you have to repeat encryption more often? Like what if you, instead of just using RSA once a day, you have to use it once a minute? Do you guys see that? So it creates a problem because that's a lot of processing that needs to happen. One of the things about elliptic curves is, well, first of all, they're considered to be secure, but also they seem to have an advantage because ECC, elliptic curves, can be faster than RSA because they use smaller numbers. Okay? And that's actually the key idea here in my discussion that I'm going to give you. All right, before that, let's talk a little bit about TLS just to frame it. So what is TLS? So you may have, as you look at your online, maybe you're curious and you study cryptography, you've come across, okay, there's something called SSL, but there's also another algorithm, TLS, right? So you're like, what is this other algorithm? Because we didn't look at the math of TLS, we only looked at the math of SSL. Well, TLS is not an algorithm or is not math. It is simply an implementation of SSL in the network layer. So if you guys remember that from your networking classes, right? The OSI model and the stack of all the layers from Ethernet all the way to the application layer. So there is a security layer, and that's called your TLS. It stands for the transport layer security. But that's just an implementation, like in the stack of the computer. But really, it's still based on all these algorithms or the math functions that we've been studying all semester, right? Which are block ciphers, AES, RSA, Diffie-Hellman, and now elliptic curves. Do you guys see that? Does that make sense? So that's a key distinction, right? So TLS is, in fact, the protocol of SSL. Very important that you don't confuse that, but still it's SSL. TLS stands for Transport Layer Security. The current TLS version, I haven't checked this like in the last few months, but should be around TLS 1.3. And TLS, the protocol handles the handshake and packet formatting for secure encapsulation of data. So it's going to have all that networking stuff. But essentially using the same math that we've been discussing all semester. The handshake relies on certificates and certificate authorities, so you guys are familiar with all these primitives now and understand why we use them. Okay? And then there's an example. So now, if you guys remember, I told you the story, right? About so symmetric encryption was pretty obvious. Then there was asymmetric, but we had the problem of sharing the key, right? We started with that at the beginning of the semester. How do we share the key? So it turns out in the 70s, Diffie and Hellman came up with this idea, right? That you guys now understand of asymmetric encryption, the key exchange, but it wasn't like the best back then, right? So then came RSA, it was implemented, it has been used for decades. Then elliptic curves were invented, and once elliptic curves were invented, they were combined with Diffie-Hellman. And so we got something, a hybrid thing, um, a Diffie-Hellman elliptic curve approach. And that is actually used today extensively. Okay. And what is the advantage of it? Well, as we stated before, ECC can be faster than RSA because it uses smaller keys. So at the end of the day, it's about performance, right? So this provides, we needed something that could be used more often, or we needed to use the mechanism of asymmetric encryption, let's say, more often. But using RSA more often meant a bit of a problem. So there's an advantage here to using something that's faster and is as secure. Do you guys see that? And so that's essentially the idea. And later today, once we move to the whiteboard, I will provide an example of the combination of elliptic curves and Diffie-Hellman for this. Blockchain also uses elliptic curves, so it's very important and considered very secure, I suppose. So as it turns out today in TLS, the current versions of TLS are actually using Diffie-Hellman. They still use RSA, but for a very specific part of the process, it uses Diffie-Hellman based on elliptic curves for the key exchange. All right. And why? So let's, we understand that one is faster, but what's the problem, right? What's the problem? So is there any particular reason to use Diffie-Hellman over RSA for key exchange in TLS? So that's kind of the question, right? So why would you need to do that? Because RSA is still secure. No one has broken RSA. Do you guys see that? But we know that Diffie-Hellman can be faster. Okay, so there's a speed up advantage maybe, but why would we need to run RSA more often, for instance? So that's really the key issue. Why do we need to do that? And the answer is something called forward secrecy. Okay, that's really what drives everything else. So forward secrecy is this problem that was discovered, right? And so because of this problem, they're like, okay, RSA is great, but we may have a solution to this problem. Although it hasn't been broken, we still need to add more security. And the way that we add more security is by running it more often. But by running it more often, it means more processing, so we need something more efficient. And ECC with Diffie-Hellman does the job a little bit more efficient. Do you guys see that? All right, so what is forward secrecy? So forward secrecy is one of those things that 30 years ago, people that were inventing the whole infrastructure of cryptography would never have thought about. It's one of those modern things of today, right? That no one would ever think, okay, let's worry about forward secrecy. All right, so that's what we're going to define now. So TLS 1.3 uses an elliptic curve-based Diffie-Hellman approach. Diffie-Hellman defines a key exchange mechanism that allows a client and a server to exchange secret keys in the presence of an eavesdropper. In a TLS connection using the Diffie-Hellman key exchange, for every new connection from a client, the server typically generates a fresh Diffie-Hellman public-private key pair that is used to exchange keys for that session. Okay, and these are known as ephemeral key pairs. So so you can see the term ephemeral, just something that goes away really quickly. All right, so we derive everything from creating a Diffie-Hellman key, essentially. So the weakness is in RSA is the private key. So here, as you guys know, we've been using the public-private key infrastructure to encrypt the secret key. But the problem is, what if you're holding that public and private key pair for a very long time? That's the risk. And that's what forward secrecy means. Okay? That somebody who knows who is collecting all of your data, encrypted, and they're saving it. And because you're not changing your public and private key pairs often enough, you're basically creating a security risk. Do you guys see that? So that's essentially what forward secrecy is. Eventually, somebody, if they break that private key, what's going to happen? They can then read all of your data in the future. No one has done this yet, but in 20 years. So if you're a government, right, and you thought that you had encrypted everything and all your secrets, and in 30 years, somebody is going to read everything that you did and know how you plan things, right? So that's the problem. So it's not even a thing that they've broken now. They're just worried about the future. And this is called forward secrecy. So the solution so far, it's almost like, when I told you guys about DES, right? They broke DES. What did they do? They just made triple DES, right? So it took longer to encrypt so that they could until they found a better system. So this is kind of the same in the opposite direction, right? So they know, okay, RSA could be broken at any time. People are collecting our data. What do? Let's change the key more often. So at least then they got one key, but not all keys, right? That's kind of the assumption. Instead of having one public key for a month, and then they break that with the corresponding private key, and now they have all your data for a month, you're constantly changing that ephemeral, right? They come into existence and go away. So the idea being in a month, maybe they got Monday and Tuesday, but nothing else. Make sense, guys? So that's essentially the idea. So we can see the notes here. But yeah, so forward secrecy, pretty important problem, it seems, especially for some people, it's a headache. And you can see it's so important that the TLS, right, transport layer of the network has been modified essentially because of this problem. So it is important, right? The fear. So here we still use the private key, but the server's long-term private key is only used to authenticate the server's Diffie-Hellman public key. Okay, thus, if an attacker compromises the server's long-term private key, they can impersonate the server, right, do the authentication part, but not be able to decrypt any previously encrypted communication. Make sense? So this is pretty important, right? So for you to understand. So remember that what does RSA provide? Confidentiality of the key, but also authentication. So it's a less serious problem if they compromise your private key and impersonate you. They can, but your secrets are still protected, right? But if they compromise the private key, that decrypts data, then that means that they, if you were using that public private key pair for a long time, they can basically retrieve all your data. So imagine all your emails, right, that or whatever, everything that you've ever written for a decade of your life, somebody has it. That's what you have to assume. It's in some bunker somewhere, and then someday somebody with a quantum computer, they also have the keys, right? So they have the public key associated with it, no doubt. So they just break it, and boom, all your data becomes available. Got it? Make sense? All kinds of secrets. So that's forward secrecy. So this is the solution. So when you think about, so RSA is still being used for authentication, things like that, but Diffie-Hellman has come in there to protect and to create these ephemeral keys. So you can see here, so thus, if an attacker compromises the server's long-term private key, They can impersonate the server, but not be able to decrypt any previously encrypted communication. Since the server's private key was never used as part of the key exchange other than simply signing the ephemeral public key. Okay? Okay, so that's the key thing. And so what is this ephemeral? Essentially, it is short-lived for the duration of the handshake with the client and then discarded. So that's essentially the key thing. It's something that needs to happen very quickly. So here you can see that these ephemeral Diffie-Hellman ciphers are on TLS on this layer of the network are Diffie-Hellman ephemeral and also which is this Diffie-Hellman ephemeral or EC, which is elliptic curve Diffie-Hellman ephemeral. All right, so these are like the protocols that are in place for this problem. So in contrast, just to kind of elaborate more on this concept of forward secrecy, in contrast, if you consider the RSA handshake in TLS, now, by the way, some TLS will have RSA, right? So remember that all of these are like a stack that's available, and so people can make their choices of which approach they're going to use, depending on the thing that they're worried about protecting. Maybe a movie is not such a big deal, right? I don't know, like a movie, but essentially, if you're the U.S. government, something like that, you might want to be more careful with this type of problem. So in contrast, if you consider the RSA handshake in TLS, the client encrypts a random symmetric key, as you guys know, to the server's public key, and the server uses its private key to decrypt and recover that symmetric key. So you guys understand that. But this allows an attacker to passively observe and store encrypted network traffic, which use RSA key exchange. So if the server's private key is compromised, then the attacker can retrospectively decrypt the stored encrypted communication. And that's it. All right, so that's essentially the danger of forward secrecy. Any questions, comments, concerns? Don't care about this at all. All right. Yeah, so you guys understand how this works, RSA key exchange, so we've talked about that. So here, just to stress, right? So you guys, understand key exchange, right? RSA really well, but actually the simplicity of the RSA key exchange idea is actually its principal weakness, right? That you have these keys, you trusted them, and you held them for a long time. The secret is encrypted with the user's public key, which usually remains in use for several years. So imagine if you have this kind of situation. You can see that the problem at the end of the day comes down to this, right? Holding that key for a very long time versus having something that you're going to be, the certificate authority essentially means you go somewhere, right? You authenticate your key. And so now, it does imply a longer timeline. So anyone with access to the corresponding private key can recover the secret and construct the same secret, compromising session security. Okay, and this, this just goes into the Diffie-Hellman. All right, so I wanted to, first of all, make this statement, right? So we talked about forward secrecy, which starts to get into this whole quantum concern, right? So they have all these ideas of quantum ready algorithms. I don't know that any of them works currently. Usually what I've seen in the past is somebody says, "Ooh, we've got this great new quantum ready algorithm." They publish it, some kind of paper. 6 months later, some lab somewhere else publishes a paper that they broke it somehow, right? So that seems to be the game. But meanwhile, they need to start to address this problem And so this is a solution. So you can see TLS using technology from today is trying to, you know, prevent forward secrecy and those things in the future if there is ever a quantum computer, which is likely in the next 5 to 50 or 100 years. All right. All right. So the key thing to remember, TLS, which is the protocol, right? The network protocol that implements SSL, still uses the same ideas of symmetric, asymmetric encryption. Symmetric is still very much AES. Asymmetric needs a key. Asymmetric exchanges the key and provides all the functionality of certificate authorities, signatures, all of that. But because of problems, people breaking keys in the future, Diffie-Hellman, which is a bit faster, has been implemented, especially now that it's been powered up and been made more secure with this idea of elliptic curves. Okay? And elliptic curves is just, we'll see that in a second, but it's essentially a way of getting numbers. Do you see that? So before, with RSA, what did we start with? Prime numbers that were really large, right? They needed to be very large because you guys already know how to factor very small numbers. And so RSA needed prime numbers that were very large to start the whole process. So we needed another, humankind, right, needed another way of obtaining numbers. And so they discovered these elliptic curves. They're essentially functions, and they have their own math operations in these curves. And so basically from there, you can extract numbers. Do you guys see that? So and it has been studied that if you follow a specific procedure to obtain these initial numbers in these curves, then it's very secure. Not all curves, as you will see in the last lecture, are secure. It's interesting. There's like, let's say 10 that have been widely studied that are considered to be very secure, but not all of them. Okay. So that is relevant to the blockchain discussion. All right. I wanted to, I always do this one with TLS and forward secrecy. Are there any questions on this? I'm not going to implement this. We're just wrapping up here. So, but yeah, this is important that you're aware of it. All right. So that being said, okay, so this has been covered. So I'm going to close that. Go back here. So we do still have the PDF, but we're going to go over the algorithm, okay, and it's really just the Diffie-Hellman algorithm that we did before. I'm just going to add a little bit of a note of what, very briefly, of just to give you some intuition of what these elliptic curves are, and it's a somewhat simple concept, okay? So I'm going to do that one. So in a past lecture, we went over the Diffie-Hellman algorithm, and we did an exercise with actual numbers where you created a number that you shared. So you guys can reference back to that, okay, for that example. Okay, and then we'll think about this later. Okay, here we are. So let's switch over to the whiteboard, and we're just going to talk briefly about, we've talked about forward secrecy. Now we're going to talk about Diffie-Hellman with elliptic curves, just to give you a very high level overview of how it works. But it should be pretty interesting. This is kind of like if there was a cryptography too, you'd go into elliptic curves, and it's very nice. It's just, it's a pretty big topic. All right, so let's talk about Diffie-Hellman So Diffie-Hellman, okay, with elliptic curve. So remember, this is what gave it the power. And in this field, in like this field of cryptography, what people will do is they'll spend a lot of their time creating proofs, right? So they do proofs, like mathematical proofs, that this is actually secure, okay? And so remember, like Claude Shannon, right, started stating what makes a secure cipher using probabilities. So there will be proofs that, that support that an elliptic curve is secure in this context. But here we just assume they are. Others have done that. All right, so let's start with sort of this idea of an elliptic curve. We've got an elliptic curve. You're going to think about that. All right, so what's the simplest curve that we can think of? Well, the simplest curve that we can think of is a horizontal line. So for instance, the curve y equal 3. Okay, so this is essentially a function, right? So it can be a curve here. So y equal 3, this is a horizontal line. So if I have y and x, right, this is 3. So that's it. That's your curve, right? Y equal 3. Do you guys see how it's obviously it's a straight line, but it's an equation that becomes uh, or a function that becomes some kind of a graphical thing. So if I have like a person that lives in this universe, right? All that they can do is they can only live here, right? So they can only go in those directions. Do you see that? And we would not draw a little person there, but instead a point. Do you guys see that? So that's the whole point. The whole idea is we create this universe governed by this curve, and then everything has to happen in that curve. If you're off the curve, then that's not secure in our context. All right, so that's the first. So that's the simplest elliptic curve. So let's look at a slightly more advanced, and you guys can tell me what this is. So here I have a x2 plus y2 equal 1. So this is what? The circle, right? It's a circle, right? So this is a circle, right, of radius 1. Do you guys see that? But what's important about this is, again, we create these shapes, and then, we have a little person that lives only on this circle, which essentially means they only live in this function x2 plus y2 equal 1. So that's the whole idea. So x2 plus y2 equal 1 is a circle of radius 1, center on the origin. So now that the little person really becomes then points. So the points on the curve are going to be known as x and y. So the points on the curve are just x and y pairs, for instance, right? So x and y pairs. And these points are the things that the numbers essentially that you're going to extract, or you're going to use them as seeds to extract other numbers. Do you guys see that? And there will be also in these curves a set of new operations, which we will see one example of just to kind of illustrate. So essentially, you're creating this world with its own operations, right? So if you've ever heard about linear algebra or when you took 265 and you learn about that linear algebra was a vector space with its own set of operations, right? Strange multiplications, additions, same idea. They created another set of math called that is curve based with operations. Okay. And it has security implications, amazingly, right? So that's the great thing about it. So the points on the curve are X and Y pairs and satisfy or live on the curve. So that's kind of how you have to think about it. They only exist within the curve. All right, so that's kind of just an introduction. So now let's get into a more formal definition. So elliptic curves typically have the form of the following form. Which is going to be y square equal x3 plus a times x plus b. Do you guys see that? So they'll have some specific, people study elliptic curves. And so usually what they're studying is something that will typically have a form such as this one. Do you guys see that? So you can see obviously here, you can create many elliptic curves, right? Just the values of A and B could be many values. But are all of them secure? No. Okay, so that's the key thing. So you have to, when I do the lecture on blockchain, I'm pretty sure I have in my notes, what is that famous elliptic curve that everyone uses for that? So for instance, you guys hear like there's Bitcoin, right? But there's also what? There's Dogecoin, maybe, meme coin, Ethereum, right? And so a lot of them are based on maybe the same curve, others are based on other curves, right? So people say that Bitcoin is valuable because it's a scarce resource. Well, it is scarce in the sense that once you've created a block, one of these Bitcoin things, the blockchain thing, right? You have only a certain number of Bitcoin that can be generated from that. I think it's like 1.4. But it's not really scarce because I can just take another elliptic curve, right? And build my own, you know, 350 coin. You know what I mean? Like it's not scarce in that sense. It's scarce once you've so Bitcoin is important because it was the first one, right? I think it was the first one by Satoshi something. Um, and so there's not really once it was created and everyone is really into it and everyone is like using it, there's no way to dilute the coins. Like I'm gonna create more coins or something like that. There's a fixed set. But that being said, you can just grab your own elliptic curve, use software, right? And build a new Bitcoin. All of you can have your own Bitcoin if you want it. Okay, so it's not scarce in that sense. But you can use, they use these frameworks. So anyway, so elliptic curves typically have the following form, and this form is known as the Weierstrass form. So this, I'll just put as a note here. This is known as the Weierstrass. Okay, so pretty important, right? So somebody started studying curves, started studying these functions. Maybe somebody named Weierstrass, and from there they started to find properties about them, and they started using them for security. So if you notice, it has these parameters A and B. So they have that form where the constants A and B define the shape of the curve. Okay? We can say that. So here, the constants A and B define the shape of the curve. Okay. So here, let's do another example. So another example of a curve be something like y square equal x3 minus 4x. Okay, so that's what is meant by an elliptic curve. So you can ask the question, does a point belong in that curve? So for instance, remember that it's all about the points that belong in these curves, right? So that's going to be the values that we're going to be using for the parameters of Diffie-Hellman. So for instance, if we have x comma y equal 0 comma 0, okay, such as that, does this value belong in the curve? So, does x comma y equal 0, 0 belong in y2 x3 minus 4x? So we can do that operation. I'll change color here. So it should be, so y is 0, right? So this one's easy. So 0 square equal x 0 cube minus 4 times 0. So 0, 0. So it does belong in the curve. Do you guys see that? So that's essentially the idea, right? So it lives in the curve or it doesn't live in the curve. So one distinction is points off the curve may represent a security risk. So you need to select points inside the curve. So let's try another one. So here we're going to say x comma y equal 2 comma 0. Okay. So does this one belong in y2 x3 minus 4x? So this would be what? 0, 8 times 2, 0, 8 minus 8, 0, 0. Right? So it should also belong. Do you guys see that? So that's the mystery, right? All right, so now the next thing, before we look at the algorithm of Diffie-Hellman in a little bit more detail, there's one more property of these curves. So you understand that it's a function that has a shape, right? And points live in it or not. But there's also one last property that they have, and that is that they have operations. And these are going to be like multiplication, adding, things like that, that only those operations are operations on the curve, and that's what adds complexity, right? So now let's say that you want to add 2 points on the curve to produce another value that's another point in the curve. Do you see that? So that's essentially the idea. So let's do a visual representation of this one. And this is going to be adding 2 points. okay, on the curve. So this is a set of math that was created just for this field. So adding and multiplying points, I'm only going to do a simple example, just adding 2 points. On the curve, adding 2 points. And we're going to call these points P and G, or sorry, P and Q. So we're going to call them P and Q. And they're just points. So imagine I have a curve that looks like this. So it's going to be, and this is a classic example. This is the curve, right? The parts that we can see of it. Do you guys see that? So that's the essentially. So then you have 2 points. You have 1 point P here, and then you have another point Q over here. Okay, that live on the curve. So just to illustrate, so the definition then of adding these 2 points is that there's going to be an operation. So we have P plus Q. And that operation actually has like a geometrical representation, which the process is something equivalent to this. So you draw a line. So whenever you want to add 2 numbers, P and Q, right? You draw a line. Trying to draw a straight line. Okay, do you guys see that? So imagine this is a straight line, okay, that you draw. And so based on that, where they intersect the graph again, so there's a definition here. So it says, the simplest way to understand point addition is to determine the position of R. Okay, this is going to be R, which is P plus Q on the curve relative to P and Q based on a geometric rule. Draw the line that connects P and Q and find the other point on the curve that intersects with this line, essentially. Okay? And then your answer will be the reflection of that. So the reflection of that would be something like this. Okay? And so let's just imagine this one here is actually P plus Q. Does that make sense? So you have a geometric shape, right? Represented by the curve, and then you have a set of operations, P plus Q, a new set of math. So when you apply it, essentially it translates to discovering this point here. Let's call it X comma Y, and this is essentially now the value that you want. Do you guys see that? So imagine how now it's obviously not just going to be P plus Q, right? It's going to be a whole bunch of math that they're going to do to find some value, and then that value is going to become your secure set on. Make sense? Any questions? So this is where elliptic curves play a role in cryptography. Okay? So once you find these values X comma Y, then you have essentially your values that you want. All right? All right, so here, and of course, from there on, believe me, the math gets pretty hairy. So this is just to give you an intuition of how it works. Okay. But the great thing about it, you don't have to do it geometrically. Obviously, you would do like math, almost like algebra, but it's a special algebra that only operates in this graph. But the key thing is it does have a geometric interpretation, and that is that, like this here, you have a line that intersects 2, then where they intersect in between, and that, you have some kind of projection to find the actual P and Q given the operations. All right, so now that we understand this, that we got the values, now let's take a look at just the algorithm itself of Diffie-Hellman and just think, okay, when we need values from the elliptic curve, we would perform some math to obtain a value such as this one, which would be considered to be secure. So instead, what is this replacing? The prime numbers that we were using for instance, in RSA, right? So that's the idea. Okay. So now let's go ahead and do an example. This is going to be more of the Diffie-Hellman algorithm. Okay. So this is going to be Diffie-Hellman for the key development with elliptic curves. So this, we can write it down as elliptic curve Diffie-Hellman. Okay. All right. So how did this work? So step one. So this is very similar. We find a value G, if you remember, right? So find a G or agree on a G. Agree on G. Two, Alice. So now I'm just going to state this in terms of Bob and Alice. So Alice picks a secret random number A. Guys over there in the back. So Alice picks a value A. Okay. Alice then is going to compute what we call the public key, if you guys remember, right? So step three, Alice computes public value A, which is just going to be G to the A. And I think when we do the blockchain example, I do have some OpenSSL or is Python maybe, and to kind of illustrate this a little bit. So it seems like there's a lot of complex math just to get like one number, but that's essentially how it goes. So Alice then, once she's computed that value, Alice sends A to Bob. Alice sends A to Bob. Okay. Then in the next step, step 5, now Bob picks a value B. Okay, so this is pretty much Diffie-Hellman. So Bob picks a value B. Okay. Step 6. Then, of course, Bob sends B to Alice. B uppercase to Alice. He needs to compute it, of course, and that is done through B equal G to the B, right? So, that was the process. Okay, step 7. Both then combine their secret with the receive to produce the key, right? The agreed key. So both then can calculate their secret, which it was something like, for instance, A to the B, keeping it simple, and B to the A, which was always something like G A to the B. Does that make sense? So this is essentially Diffie-Hellman, sort of what we did before. Okay, but that's how we establish the key exchange. So now elliptic curves are just used. They were just like added so that some numbers can be calculated. So now let's take a look at that. So let's do now elliptic curves modify as follows, right? So now let's just say now we add elliptic curves. So what do you have to do? First of all, find an elliptic curve. So just to keep it simple, I'm going to grab one of the ones we've used. So, identify a secure elliptic curve. Right, so this is step 9 plus AX plus B. So this is really important, right? Not all elliptic curves are secure. So pick one. That is secure. Okay. And then what are you going to do? Probably start at a point in the curve, perform some of those operations that I showed you, like the addition, multiplication, and then that's going to take you to another point in the curve, and that point becomes your value. Do you see that? So that's how you extract numbers from the curve. Okay. So now let's think about the algorithm. Oops. All right, so we did the calculation. We're on step 9. So now with elliptic curves, we have to find a point G on the curve. Okay, so that's essentially the idea. So step 10, find or calculate, find some fixed point and we're going to call it G, uppercase G, on the curve. Okay. All right. And then given that number that they're both going to use, Bob and Alice both use that number essentially. All right. So for some fixed point G, now Alice will select or picks a number such as DA. Okay. Then Alice computes her public. So she's going to, so let's say Alice computes PA using DAG, where remember before G was coming just from some set of values that you had available. Now the G uppercase is coming from the elliptic curve itself. Okay, that's essentially the idea. So this is from the curve. And so she calculates this value. And then after that, you can imagine the algorithm is pretty similar. So that's really, in its simplest form, the contribution. So of elliptic curves. So now Alice sends PA to Bob. Okay. Then next step, Bob picks a value, which in this case is DB. Okay. Then Bob computes PB, which is going to be dB times this G, which is from the elliptic curve. Do you see that? So that's essentially the idea. And then, of course, at that point, they can calculate their keys. So Bob sends Alice PB. So Bob sends Alice PB. Okay. And now both can compute their shared secret. They can use that or use that as seed to develop deterministically other parameters, like we did with the round keys, if you remember. So in this case, the last step, both compute the same secret. Same secret. So it's going to be what? dA PB, right? For Alice, which should be equal to dB PA for Bob, right? And they have, which translates into dA dB G from the elliptic curve. So in its simplest form, this is how it works. Any questions? Do you guys see that? So here, it's very nice because, we use Diffie-Hellman, but increase security by using an elliptic curve, a much more complex process of extracting initial numbers for this. All right, so that's essentially the idea of it. Okay. Once I do the blockchain lecture, I will in Python illustrate with some code some of these ideas so that we can see it full circle. OpenSSL also, you guys could, so I may add this later as an OpenSSL example for you to just exchange keys with elliptic. So remember, the algorithm is called EC Diffie-Hellman. So it's ECDH. And that's, I think we had it on the GitHub. So we had it on the GitHub. All right. So what time is it? 5:17. So if we can start the VM or I can save the VM. Should we start the VM right now? Yeah, let's do that. Let's do the VM. And we can just play with these ideas a little bit and then wrap up by discussing the homework. All right. Remember that some of you will be working on this homework assignment on your own, especially if you've already demoed. Okay. I remind you, for those of you that haven't demoed, please be ready this Thursday to do your demo. Any questions? Yes, please. I will probably go over the lab first, just real quick, if I don't get to do it right now. All right, so let's switch over to the virtual machine, and also we can start it up. We do have some time, so. Yeah, there, right. So let's start the virtual machine. And yeah, so what we're gonna do, start the VM, play with a few of the commands that were already on the GitHub, and then also just talk about the homework assignment for you guys. So, but we've like the theory of elliptic curves we finished, right? And the implementation of elliptic curves and Diffie-Hellman together. Did I not? Okay. All right, so let's while it's doing that, let's just go back here. So we're gonna click on this one and so here, right? So remember, we started our conversation today with OpenSSL, which led us to TLS, and we mentioned that TLS for, some implementations for security reasons, such as forward security or forward secrecy, uses this idea of elliptic curves with Diffie-Hellman. Okay, and so then we went over the algorithm briefly. So you can see here, there's a few commands, such as this one. This is ECD some version, right? So we can run that. Give me a minute. Well, while that's happening, I'm going to also open up the homework. So remember, especially for everyone, especially those that have already demoed, this is your assignment for this week. Before I forget, I'm just going to add the assignment link. And I'm going to give you 2 weeks for this one because of the Thanksgiving break. So let's go ahead. This I'm going to call OpenSSL HTTPS. So that reminds me of what this is about. Essentially, it's the HTTPS protocol, right? You guys are familiar with that. You know that in the background it's doing the whole SSL. Okay, so that's gonna be due on the 4th. Okay, at 10 p.m. is fine. Let's say complete the attached PDF. And the tasks are, we need to, I think it was just everything, what is it, tasks 1 through 3, right? And excluding task 4. If there's any other one. All right. Now, and it's going to stay open. Oh, this one, leave it open until 7th. Any questions, guys? So this is, yeah, so we can look at the PDF for a sec. Okay, so task 1 through 3 should be correct. So you read, the way that this works is you read through this, right? So I'll read through this one. Some of these concepts you should be familiar with. You're not going to do any man-in-the-middle attacks, I don't think. But you guys understand we've discussed this already theoretically how it works. This relates to TLS, which I've discussed. So the tasks are here. Task 1, becoming a certificate authority. So that's you guys becoming your own VeriSign. You can, right? With the power of Linux and your knowledge of RSA, you can become your own VeriSign. Become a company that does just this. All right, so that's task 1. Let's say that some people had like paintings, right? And the paintings have to be authenticated. So you guys could take a picture of the painting, scan that as data, sign that, and then you're a famous authenticator of paintings. Do you see how you could use this for many different ideas? But anyway, you can use this framework for that. All right. So task number 1 is to become a certificate authority, CA, your own VeriSign. So you have to do that one, obviously. Task number 2, you're going to create a certificate for seedpkilab2020.com. So that's essentially because if you're Amazon.com, right, you actually have that domain. You own Amazon.com. So when you go to register your public key, that's going to be part of your what you're signing, right? They'll sign Amazon.com, not some other website, but that one. So that's part. So you guys will do this step by following these instructions here. And then task number 3, deploying the certificate in an HTTPS web server. Instead of using Apache or something like that, you're just going to use these commands over here. And OpenSSL has a feature of creating a server, like a web server, just for simulation of cryptography. Do you see that? So it's way easier than having to configure something like Apache web server. That's more of a term project kind of thing, if you're interested in that. Okay, is that clear? So you will follow these instructions, complete task number 3 here. And that's it. Once you get, this is step 4. So this is like where you prove that it works. And then you can skip everything from task 4 on. So if you notice, this one says deploying certificate in an Apache-based HTTPS. So that's an entirely different problem. Is this clear, guys, for everyone? This is actually a really nice lab. You will learn a lot from this lab about how your little browser works, right? And how everything, it should be very interesting, right? You don't actually see the algorithms because you're just using OpenSSL commands, but you now understand what's happening behind the scenes. Okay? But it's an example of how HTTPS works. The client is what? The browser. So Mozilla Firefox in the VM is going to be your client. So that represents your laptop, your Mac, somewhere in the world. And then you have a OpenSSL will, when you run this command here, will become its own web server. So it's essentially now like localhost with a host, with was a port number, right? Yeah, so it's going to be an open port. And so when you make connections to that, it's like it was port 80. Do you guys see that? So that's essentially the idea. Notice you're using keys like server.pem, etc. So that's the process. And then, as I said, task 4 deploying, that just assumes you're using Apache. That's a different kind of configuration. You can skip all of that. So there's a task 5, the man-in-the-middle attack. Again, this is more project level things because you have to use Apache for them. And task 6, so yeah. And then the submission as usual, provide a report with screenshots. So only steps 1 through 3. So let me make sure that's clear in the notes in the assignment. So complete the attached PDF, task 1 through 3, excluding task 4 through 6, let's just say, because I couldn't remember. Is this clear enough for everyone? Perfect. All right, so I'm going to load it, so that's done now. All right. So let's take a look at the VM. So it did finish. There's just like one command, but I want to run it. In the cryptography, we just had this OpenSSL speed test. We've been doing this, right? We did this last week. We did speed test of RSA versus AES, if you remember, in various ways. This is more benchmarking RSA to elliptic curves, okay? Elliptic curve Diffie. So let's try out this command. Should be OpenSSL. For that, yeah, so we're going to try this out here with OpenSSL. Okay, perfect. So we have a speed test. And it's doing pretty much what we did before, where we were comparing RSA and AES, but now the other two. So let's give it a couple of minutes to finish. What do we observe? Okay, so here in the sign seems to be a little bit faster, right? 3 zeros versus 1 0. Verify. Or is it signatures per second? Is that how you guys identify this? Right? Signs per second? Yeah, so more, right? So uh you can do more. Okay. Yeah, so the keys do seem to be smaller, which implies that this is also they have equal security, but smaller number of bits here. All right. Any questions, guys, on this idea? No questions? All right. So that's essentially, one of the important conclusions here with cryptography, right? Performance has always been important as you're choosing your algorithms. All right. So let's wrap up today then just with the PDF essentially. So let's take a look at it. All right, so let's kind of walk through it. What are you going to do? So public key cryptography is the foundation of today's secure communication, but it is subject to man-in-the-middle attacks when one side of the communication sends its public key to the other side, right? So that's the motivation for having a certificate authority. The fundamental problem is that there is no easy way to verify the ownership of the public key, right? We've established that. I.e., given a public key and its claimed owner information, how do we ensure that the public key is indeed owned by the claimed owner? So this is where the public key infrastructure, PKI, is a practical solution to this problem. So the learning objective of this lab is for students to gain firsthand experience on PKI. So by doing the tasks in the lab. Students should be able to gain a better understanding of how PKI works, how PKI is used to protect the web, and how man-in-the-middle attacks can be defeated by PKI. So students should understand the root of the should be able to understand the root of the trust in the public key infrastructure, because you will be the root, right, of the trust by creating your own certificate authority. That's, you're the root. In this lab, you're not using VeriSign, for instance. You are becoming your own VeriSign. And what problems will arise if the root trust is broken. So the topics cover are public key infrastructure, public key PKI, certificate authorities, and root CA, the certificate X509, these PEM files, we've already covered that. And this is called a self-signed certificate. So you guys may have heard this term before somewhere, right? A self-signed certificate is what you're doing because you're the signer. But think about it, if you're the IT person for a company in the intranet, that may be something you want to do, right? For added security. Do you guys see that? And so in Linux, of course, and OpenSSL are solid tools, right? So these are, in fact, of all the things in cryptography we've done, you can trust OpenSSL. All right, the ideas, we're exploring this protocol of HTTPS. Remember, HTTP is not encrypted, but it's the protocol of the internet. And then HTTPS just uses encryption. Okay? So that's that's the motivation. So these are the steps. Essentially here, one thing I will recommend for this lab that may cause you a lot of problems, when you do this step here, you see how there's a little dot there and then demo CA. Dot just means current working directory in Linux. Okay. But sometimes I've noticed students get this wrong completely. And then when they try to do this, they can't find the files for whatever reason, or they're being written in strange places. So my suggestion is to put in the full path here instead of the dot. Okay, so start at root, home, seed, whatever it is, and make the desktop, like the central location of everything. Does that make sense? So you have to pay. First of all, when you're doing this lab, it's not hard, but concentrate. Don't watch the sport, your baseball game or something like that. Because there's a couple of steps where you can make a mistake, and if you mess up one thing, you have to restart again. That's unfortunately the downside of this lab. It's one of those, right? You have to configure a lot of things correctly for it to work, but it's not difficult. Just concentrate. So common things, as I said, students, just put in the full path here. So start with the desktop. You're going to have to create these folders and files. So you need to create 3 folders, which are going to be certs, this one. So it's just creating a folder on the desktop. You can actually create a folder called demo CA, and then inside that put in everything. Okay, so that's not too difficult. So then folder certs, folder CRL, and folder new certs. So when you're running the OpenSSL commands and everything, it's going to create files, and they need to be in the right places. Then you're going to have to create 2 files, which are index.txt and serial. And for one of these files, you should create it with the command called touch. There's a command called touch instead of nano, because it'll say in the instructions that you have to create an empty file that has size 0. And if you create it with nano, even if you put a space in there, it's not going to be size 0. Okay, so we have the terminal open here. So what I mean by this is, let's go to the desktop. So let's say you need to create a file. Let's call it temp.txt. So you do touch, I believe. Okay, so I do ls-l. Do you see that I created the file called temp.txt, but if you look at the size, it is 0. This is key. If you don't do that, it's not going to work. Okay. For the other one, I think index, I think you just have to put in like 1,000 in there, so that nano should be fine for that one. Got it? So these are the biggest problems that I have seen in the past for this lab. So create the folders in demo CA. Don't use the dot. Put a full path. The dir here just means this directory. So you're establishing where everything is located. Says here for the index file, simply create an empty file. So actually it was for index. For the serial file, put a single number in string format such as 1,000. Okay, so you can use nano for that one. Otherwise, just follow the instructions carefully. Make sure, oh, there's going to ask you for passwords. Just use D's for everything because security is not an issue. Otherwise, later you won't remember what the passwords were. And make sure that you sign the domain that you're going to use later on. Otherwise, it won't work. Okay? Yeah, so you'll be creating files, the certificate files, the server files, the public files. You'll be signing them. And then you're going to start up the web server with all the information and you're going to test it. So what I need to see in the report is that you get to the actual final page, but make it very clear that, because there's a couple of ways to get there. One is it's going to give you that page that says, this is not trusted, get out of here. But if you click add exception, it will let you in. But that's not the right answer, right? So what you want is you want to configure everything correctly so that when you go there, it automatically takes you to the page. Got it? This is a common thing students do. They add the exception. I can literally see it in the report, and you're going to lose the points because that's wrong. Everybody understand? All right. So that's the lab. As I said, it's mostly a tutorial. Those are the common problems. Should be a fun one. Just pay attention to it. The tutorial is really good, but just, be careful. All right, guys. So it is 5:42. All right. So we're almost that was the last algorithm, essentially. And what we have now left is applications. So denial of service and malware. Yeah.
Homework, or is there going to be another homework?
That's a good question. So this OpenSSL is homework. Next week is Thanksgiving, so no homework. The following, the week after Thanksgiving is the scavenger hunt, which is not a homework. You do it in class. So yeah, this may be actually your last homework. All right. All right, guys. Have a good rest of your day. I'll see you on Thursday. Remember, some of you still need to demo. Be ready for them.